A few years ago, my math teacher was talking about what mathematics meant for him. He told us that math is learned for us not to get fooled. That stuck with me. Fast forward to today, I see trick after trick being pulled on people on a daily basis, and nobody really notices. Or better said, nobody cares. And I get that. It's definitely a hard task to know how to use math against scams, let alone want to. But that's what I'm here to teach you today. As I was saying, many people nowadays are scammed on a daily basis, and there's one scam that has evolved and stayed throughout the years. That being gambling. Yes, let's spend money to magically earn tons through the power of luck. Or luck anyway. Like, how much luck would you actually need to gain from your gamblings? Well, I want to talk about something that went viral about 40 years ago. Plinko, which is based on the game Pachinko but adapted to the digital world. If you don't know what I'm talking about, good for you. You'll learn it here. Pachinko is a Japanese game which is basically pinball plus slots. You put money inside the machine, which awards you metal balls that you can then launch with a lever, and then they fall through a triangle of pegs and land in different areas that award you money, which probability to land in is either decided by the machine or simply decided by math and physics, the same way that dice are either loaded or just decided by the way you throw them and math. Plinko is basically this, but also online and more gambly. The areas you land on multiply your money spent by the number in said area, which is not a good thing. Let's imagine that the website decides to leave the game as it is. Just let math do the work. How do we calculate that? Let's imagine we have one ball. It can fall either left or right, but both sides have a 50% chance for the ball to fall into, which is the same as saying that one out of two times the ball will fall to the left, and so with the right. Cool. Now let's imagine another row. Now that the ball has fallen to the left or right once, if the ball has fallen to the left, it'll be less likely for the ball to fall to the left again. It's like getting two sixes in a row when throwing a die twice. Don't get me wrong, the chance to fall to either side is still the same. We're just taking in consideration the last fall. And if you fall to the left first, it's more likely to fall to the right next time, the same way that it'll be more likely to get anything other than a 6 after getting one before. This is calculated by multiplying the probability by itself. 1/2 times 1/2 is a quarter, or 1 times out of 4, which is the probability to fall to the left twice in a row. The same goes for the right. By now, you should be able to see the pattern. If we keep going, all we really have to do is multiply the fraction by itself, over and over again. Which, if we want to keep simple, is that fraction to the power of the amount of times we need to multiply the fraction by itself. We'll call this variable n. So we have 1 divided by 2 to the power of n, because that's the only thing that keeps augmenting exponentially, not the enumerator. This is important. Our variable n is related to the row of pegs the ball is in, except we don't count the state where the ball hasn't passed through any pegs yet. We call this state row 0. In that case, n equals 0. This makes sense because the ball has a 100% chance to be there. There's not a possibility where the ball just doesn't appear at all. Let's prove it though. When n equals 0, we should do 1 divided by 2 to the power of 0, which is 1. Multiply that by 100, and you get our original 100%, just like we said. And then, we can also check the next row, being n equals 1. When n equals 1, we should do 1 divided by 2 to the power of 1, which is a half. It is worth noting that we should not put n as any value under 0. That being because there's no rows that are called -1 or -2 or -3, and there's just no use for that as of right now. Alright, now that we have our formula proved, let's take it to the real world. Imagine this scenario. There are a total of 12 rows, which means that we'll have to multiply our fraction by itself a total of 12 times, which ultimately means that n equals 12. Now we just have to solve. 1 divided by 2 to the power of 12 equals 1 divided by 4096, which is that. Although that's the decimal, if we want the percentage, we just need to multiply it by 100, which is approximately 0.024%. That's the probability of landing on the left edge. If you want to add the other edge, just simply multiply the result by 2, which would be around 0.05%, and I'm rounding it up. Now that's only 2 of the landing spots that could earn you any money, and they are the hardest to land on. But what about the others? Which are a few, by the way, exactly 6 more. Seems a bit reasonable, right? To calculate the probability of those, we need to take a look at Pascal's triangle. In reality, there are multiple ways of calculating this, but all of them somehow reside inside the properties of the Pascal's triangle. First of all, if we take a look at it, we can see how the numbers are related to the calculation we did before. This is because the denominator we were using was determined by the sum of the values in each row. For example, 1 plus 3 plus 3 plus 1 is 8, which was the denominator we were using in the third row, basically 2 to the power of 3. If we keep this in mind, we can already guess what the probability to land in the middle will be, but we still need to generalize our formula. How would you write a formula that refers to the Pascal's triangle values? Well, there's plenty ways, but I decided to refer to them as combinatorial numbers. You see, Pascal's triangle hides a lot of properties. The powers of 2, the powers of 11, perfect squares, the Fibonacci sequence. I could make a whole video about it, but I believe that subject has been touched enough by the internet. One of the most fascinating traits is that it contains combinatorial numbers. These are extremely useful for us. For the time being, we only need to know that these are tags that we can use to name any number from any row without ever having to use Pascal's triangle and sum all the way through our answer. We just need to use what we call n choose k. If you have any issues on the matter, in the description there's a really short and neat video that helped me out so much while making this video by the YouTube channel The Bright Side of Mathematics. They upload videos daily surrounding many topics in math, sometimes short, sometimes more lengthy, but all of them are extremely useful, and I cannot urge you enough to watch their content. Where were we? Yes. Combinatorial numbers are only the result of n choose k, which is called the binomial coefficient. N indicates the row the number is located in, and k is the number from the row, or better said, the entry from the row. Now that we know this, we have found ourselves a beautiful formula. N choose k divided by 2 to the power of n. That, my friends, is our golden ticket. It's our way to calculate the probability to land in any entry from any row, without ever having to go through the lengthy problem that is calculating late rows in the Pascal's triangle. Let's try it. I want to give you the full answer. Here are the different calculations for each and every area you can land in this Plinko. Now that's all the areas that could earn you anything, so what about the rest? The penalty to land in those areas in this scenario is either losing almost half of your money inside the website, or let alone losing 80% of it. Seeing that anywhere that does not punish you only has around 15% chance for the ball to fall into, it's safe to say that this is obviously not profitable. Either way, around 85% of the times you play this, you'll end up losing half your money spent, or worse. In fact, here's a list. Doubling what you spent, around 11% of the time. Multiplying it by 8, around 3%. By 24, not even 1%. And by 177, 0.05%. Losing half of your money, around 24.2%. Losing 80% of your money, 61.2%. In conclusion, Plinko is without a doubt not worth playing. You simply need to play around 10 times to double what you spent once, around 33 to multiply by 8, around 200 to multiply by 24, and around 2000 to multiply by 177. Nowadays, Plinko usually comes with crypto prices and whatnot. It's irritating to see that people actually fall for it and actually play it. But it's like getting mad at casino. They exist for a reason, and if you're watching, at least I believe you do know why. Thank you so much for watching. I hope you learned something, and I hope you had fun, because at the end of the day, that's what math really means to me. And teacher, if you ever see this, you know who you are. Thank you. This is the credits, by the way, you can just leave at any moment. Thank you, Mates Mike, which is a Spanish math divulgation channel, which made a video explaining how they made their content. That helped a lot when making the video. If you know Spanish, it's worth watching his content. It's really entertaining. Thank you 3 Blue 1 Brown and Leios Labs for making this contest in the first place. We wouldn't have done this otherwise. This video has been worked on by 2 different people, me and Ioné, who helped me a lot with support and editing the funny video and making the cute little stickman. My name's Luca and I did the research, the more mathematical visuals, and the script, and the voice you hear right now. Keep in mind that we're only 16 and we're both Spanish, so take any data we've given you with a grain of salt. If you notice something's not quite right, please leave it down below. I'll try to read everything and just pin it, or maybe even edit the video after release and point out the things where we were wrong. We're all here to learn at the end of the day. Well, that's enough for the credits. Yet again, I hope you enjoyed it. Until the next time.